In this video, we are going to look at Friedel Craft, acylation and alkylation and the mechanism that is involved in this reaction. Kindly like and subscribe to the channel after watching so that you will keep in touch with every update that's come from this channel. Let's begin with the tutorials. So, Friedel Craft is acylation, which is the first one we're going to treat. It's an electrophilic substitution reaction in which an alkyl group is introduced into an aromatic ring in the presence of an aluminum chloride or ferrous chloride. So the reaction, the benzene ring or an aromatic compound is treated with an alkyl halide. So an alkyl halide is a hydrocarbon has lost one, whose one hydrogen has been replaced by a halogen. A halogen is any of the group 7 element, being chlorine, fluorine, bromine, or iodine. So when a hydrocarbon, that is alkanes, are replaced, one of the hydrogens are replaced by a halogen, we call it an alkyl halide. So in Craft acylation, alkylation, an alkyl halide is used to treat an aromatic ring in the presence of an acid, and the acid is either aluminum chloride or ferric chloride. So let's go straight to the reaction that involved and the mechanism that goes in Friedel Craft acylation. Then we proceed with the acylation. So this is an example of Friedel Craft acylation, where an aromatic compound, and this one is a benzene ring, is treated with an alkyl halide. This is an alkyl halide in the presence of this base, aluminum chloride, to yield an alkylated benzene or alkylated aromatic compound and an HCl. So this is a simple reaction that is involved in Friedel Craft acylation. So let's look at the mechanism that is involved in this reaction. In Friedel Craft acylation, what happens is the alkyl halide basically loses the halogen, that is the chlorine, to the base. So here, the methyl chloride plus the aluminum chloride, this one will act as a base to the methyl chloride and abstract this chlorine to itself to produce an aluminum tetrachloride with a negative charge, which leaves a positive charge on this carbon. So this is a charge. This positive charge makes this compound or this radical an electrophile. An electrophile, as we said, is an electrophilic substitution reaction. So this electrophile is used to substitute or replace one of the hydrogens on the aromatic compound. This one acts as an electrophile and attack the nucleophile, which is the aromatic compound. This compound is nucleophile because it has the localized electrons in its system. So this one will attack. The compound would attack the positive charge and form this. So when the benzene ring attacks or takes a positive charge as the carbocation or the carbocation, it leaves a positive charge that the pi bond system in here will break onto the adjacent carbon, leaving here positive charge. Next, the aluminum tetrachloride with a negative charge, one of the chlorines will abstract this hydrogen and form an HCl with it. When this chlorine abstracts the hydrogen, we are going to leave this catalyst there, which we started with. Then the double bond will form back. So at the end of the day, we are going to have an alkylated aromatic compound, in which this one has been used to replace one of this hydrogen. That's why we said it is an electrophilic substitution reaction, because an alkyl halide or an alkyl group is used to, which an electrophile is used to replace one of the hydrogens on a benzene ring. That's how the mechanism works. Let's take a look at an example. This one did the same reaction, but here with different mechanism altogether. If this one is added to this alkyl halide, we are going to create an intermediate positive charge, which is this. So the aluminum chloride will abstract this chlorine and leave a positive charge here. Now, because of this one, a carbocation which is unstable as compared to a secondary one. This one is a primary carbocation, but secondary one is more stable. There is going to be a rearrangement where one of these hydrogens will be shifted to this one, and this plus charge will come on this carbon. So here the rearrangement occurs that the plus charge will come here because of the higher stability of, I mean, positive secondary carbocation than primary carbocation. Then having this secondary carbocation, the mechanism will proceed. This one attacks this, then we produce this one. So it means if there is a possibility of reforming a primary or even tertiary carbocation, there is going to be a rearrangement. And based on stabilities, tertiary are more stable than secondary, and secondary are also more stable than primary. In other words, if you have a possible rearrangeable, compound, but you don't want the rearrangement to occur, you have to use a ferrous chloride. So FeCl3 will also go by the same mechanism, but here there is no going to be no rearrangement. So that's how it works. It's going to give the alkylated aromatic compound, but there is no rearrangement. But when you use aluminum chloride as the catalyst or the base, you are going to have the rearrangement occurring. Let's go next to the Friedel Craft acylation. So for the acylation, we add an acyl group to aromatic compound, but with the acylation, we add an acyl group. An acyl group is an acyl group that is an acyl group bonded to a carbonyl group. So just like an aldehyde that has lost one hydrogen, which forms a carbonium ion, which is a plus charge. This one will act as an electrophile and attacks the benzene ring to form an acylated aromatic compound. So let's see. That's how the mechanism works. When this one is treated with an aromatic compound, this is an acyl chloride. The same thing, the aluminum chloride will abstract the chlorine. And when it abstracts the chlorine, it forms the aluminum tetrachloride with a negative charge and also a carbonium ion, whereas a plus charge. So here this one acts as the electrophile, coming to attack the nucleophile, which is the benzene ring. The benzene ring is a nucleophile because it has electrons, several electrons in it, want a positive charge. And this one is the carbonium ion with a plus charge is an electrophile. So electrophile, the name implies electrophile. This is an electrophile, or these ones are electrophiles because they have affinity for electrons. The plus charge means that it has more protons than electrons, therefore it has affinity to attack any electron, rich species. That's why we say electrophile, or the name electrophile means it likes electron. So philic means like, and electro, it means it likes electron because it has more protons in its system. So here the carbonium ion will act as the electrophile, and the benzene ring, or let's say the aromatic ring, will attack the carbonium ion, and we form this. And as the mechanism goes, if the benzene ring takes the carbonium ion with the plus charge, this pi bond system will break into the adjacent carbon that is holding the double bond, the pi bond system with a plus charge. Next, the aluminum tetrachloride will here act as a base because it has a net negative charge that the chlorine is took from the acyl chloride. That chlorine will act as the base and abstract this hydrogen just like it did for the acylation, so that we initiate the double bond between here. So that's the difference between acylation and acylation. They all go by the same mechanism, but for the acylation, we treat an aromatic compound with an acyl group, but with the acylation, we treat an aromatic compound with an acyl group. Bear in mind, acyl groups are, these are acyl groups, that is R. This R represents any chain with carbon double bonded to oxygen. This is an acyl group which can be derived from acyl chloride. So this one is used in the Friedel Craft acylation, but with the acylation we add an acyl group. This is an acyl group like the methyl chloride to the aromatic compound to initiate the carbocation, which is the electrophile, and the benzene ring will take the electrophile and form an alkylated. So that's how Friedel Craft acylation and alkylation works. It just involves adding in the presence of. Kindly subscribe to the channel after watching. Thank you.